Recording. Okay, so today is the last day that we're going to have a lecture starting next week. As you know, we have exams, okay? So on Tuesday is test 4, and then if you want to take the final, that will be on Thursday, okay? If you have questions, you can talk to me after class. Okay, so last time we talked about power series, and then we looked at properties of power series, and we actually figured out some power series for common functions. So I have a list here, and then today, throughout the day today, this list is gonna make more sense completely. But so far, part of this list should make sense to you already. So we have seen this function, right? So we found the power series for this function, and we know this from a long time ago. It's just geometric series. And then I kind of hinted that if you have e to the x, you're gonna get the function, this power series, x to the n over n factorial. We're gonna see exactly that today. So the next two we're gonna see today. But last time we saw this one, which is equals this guy. We saw it, and we saw the inverse tangent. Okay. So far we have seen these three for sure. Now our discussion today is going to allow us to understand, e to the x sine, cosine, and then this one's called the binomial. Okay. So this is called binomial series. We call this the binomial series. Right, so we already know 3, so our discussion today is going to lead to the rest. All right, so what's going on here? So in this section, we talk about Taylor and McLauring series, and this is basically just a name that we're going to give to the power series, because power series, they have a general form, and that's what we want to investigate now, okay? So let me write this down. So let's suppose that we have a power series. I'm going to call it f of x. And we can call it a function because in its interval convergence, it can be considered a function. So let f of x be the sum from 0 to infinity of an times x minus c to the n. So let this be a power series centered at c. Okay, centered at x equals c. Now, of course, this is defined on some interval, right? On some interval, and moreover, we know that this interval has a form c minus r, comma c plus r, plus or minus the endpoints, and potentially r could be infinity. Okay, where here r is the radius of convergence. We know all of this. And it could just be a point, okay? It could just be that it's centered at C and it's only defined at C, so that's fine, okay? All right, so suppose that we have this power series. The question is, can we say something about this coefficient? Can we figure out what an is? This is what we want to do. So the question, can we find a formula for an? Okay, that's really all we need. So if we can figure out a formula for an, then we'll be able to find power series for any function that comes our way, given certain conditions. Okay, so let's try to figure this out. So how does an looks like? Of course, in terms of the function f is what we're trying to do. So note. So by the way, the answer here is the answer is yes. So let's find it. So the idea is the following, that f of x is a power series, right? So we have this power series. So what that means is I'm going to span this out. So this is equal to a0 plus a1 times x minus c plus a2 times x minus c squared plus a3 times x minus c cubed, and so on. Okay, that's what the power series is. And our job now is to figure out what these guys are. Was a0, was a1, etc. And then the observation is that when we have this function, we can take derivative of this, right? So remember, we said that power series can be differentiated, and the idea is that f is infinitely time differential. So f can be differentiated as much as we want. So as many times as we want. So let's take advantage of that. Okay? So for example, if we want to figure out A0, what can we do? How can we find the value of A0?
Setting x equal to 0 or setting x equal to c.
Exactly. So if we plug in c into the original function f, what's going to happen? All of this part right here that has the term x minus c, they're going to go to 0, and we end up with A0, right? So note, if I plug in c into the function, what do we get? We only get A0. Yes? So we have that A0 is going to be equal to the value of the function at c. Now, if we want to figure out A1, what can we do? Well, I cannot play this game because this game will only give me A0. So what we can do is, instead of looking at f, we can look at the derivative of f. So we can consider the derivative of f, and you will see in a second why. I already know A0, so I don't care about it. So when I take derivative, this goes away, right? It becomes 0. And then what's the derivative? What's the derivative?
A1.
That would be A1 plus 2A2 x minus c plus 3A3 x minus c squared. Let me write the next one. Then the next one was A4 x minus c to the 4. So that would be 4A4 x minus c to the 3. And so on. Yes? So now, once again, we can play the same trick. If I now plug in c into the derivative, all of these terms are gone, and we end up with A1. So f prime of c, that's going to give me A1. So far, so good. So now we're going to keep playing this game, okay? So now to find A2, what are we going to do? We take the derivative of f prime, right? That's going to get rid of this A1, and then this coefficient here is going to give me, this term here is going to give me 2A2, and the rest, because you decrease the power by 1, the x minus c survives, so when you plug in c, it's gone, right? So the second derivative of the function is going to be equal to 2A2 plus, now, what do we get in the next term?
6A3.
So 2 times 3, remember, we're looking for a formula, so let's not multiply. So we get 2 times 3A3 x minus c plus 3 times 4 x minus c squared, and so on. Yes? So now, once again, if I plug in c, which is the center, what's going to happen? All the x minus c's are gone, and then we get 2 times A2. Yes? So I'm going to do one more. Now, to find A3, what do? We again, the same idea. We take derivative, so it's a constant, so it's gone, and we are left with this coefficient because this is the coefficient of the degree 1 term. And then every other term, there will still be an x minus c left over. So when we plug in c, they are gone, right? So the third derivative is going to be 2 times 3A3. And then what remains? That will be 2 times 3 times 4 x minus c. Let's see, who can tell me what's the next term?
Isn't 2 times 3 times 4 times A4?
Yeah. Yes, there's an A4 here. So who can tell me what's the next term?
5 times 3 times 5 times 4 times 3 times A5.
So this is A4 x minus c. Now plus, so what would this be?
3 times 4 times 5 A5 x minus c squared.
X minus c squared, and so on, right? Okay, so now when we plug in the center, everything that has an x minus c is gone, so we get 2 times 3 times a cubed, a sub 3. Yes? Now let's try to see if we can figure out the pattern here. So what do you think is going on? So first of all, here it should be clear that notice that 2 times 3 is the same thing as 3 factorial, right? Because, I mean, you can think of a 1 being there even if it's not there. So we can rewrite this as 3 factorial times A3, right? On a similar note, 2 is the same thing as 2 factorial. So you can think of this as 2 factorial times A2, 1 factorial times A1, and even this one. You can consider this as 0 factorial times A0. Point is that the factorial here matches the index. You see? The factorial matches the index. And also matches the order of the derivative. So 1 factorial and we have first derivative. 2 factorial, we have second derivative. 3 factorial, we have third derivative. Okay? So, for example, if we wanted to figure out the fourth derivative of the function evaluated at the center, what would this be equal to?
4 factorial A4.
It would be 4 factorial A4. And indeed, that would come, let's see, that would come exactly after we did this derivative, right? And then that would be exactly this coefficient. And this right here is 4 factorial, right? So notice that every time that you take derivative, the term that has the linear, in this expansion, the term that has the linear term x minus c already has the factorial completed. The next one is missing one guy to get the factorial, which is going to come up when you do the derivative one more time to get the following one. Okay, so this is going to keep on happening. So hopefully it's not hard to see that if we keep doing this, then we can say that the nth derivative of the function evaluated as c, which is the center, is going to be equal to n factorial times an. Okay? Or, in other words, an, which is the coefficient that we want, equals the nth derivative of the function evaluated at the center divided by n factorial. Do you understand this? And this is valid for all n. In particular, notice that when n is equal to 0, we have the zero derivative of the function. By definition, the zero derivative of the function is the function itself. So the zero derivative is just f. Okay? All right, good. So the moral of the story, in fact, this is the theorem, right? So we have here is theorem. And what we just did was the proof of that theorem. So if f of x is represented by a power series, if f of x is represented by a power series in an open interval I, so in other words, what I mean by this is that we can write f of x as a power series. Okay, then we just saw that the coefficient has the form the nth derivative of the function evaluated at the center divided by n factorial. And so we can write that f of x equals sum from 0 to infinity. Now instead of an, we can now be more specific. This is the nth derivative evaluated at the center over n factorial times x minus c to the n. Okay? So that's what we just saw above. And in fact, this is due to Taylor. Okay? So this, what you see here, we call this Taylor series. So given a function f, we can now make this definition. We need to make sense of what does it mean to write down equality here for another function. Notice that here I'm writing equality without any worries because we started with a function f defined as a power series. Okay, so there's nothing wrong with writing this equality. But now if you start with a function, let's say the sine function or the cosine function, you have the function, then you can play this game and you're going to get a power series. The question that remains is, are the two things the same? That's something that we need to discuss somehow. Okay, so every power series has this form. That's what we have proved so far. For example, before I even give the definition, we already know the power series for our tangent, right? So notice that f of x equals, let's say that we have f of x equals arctangent of x. Then in this case, if you remember from before, so we did arctangent right here. So last time we figured out that the power series for our tangent, right? And remember the trick, it was we took the derivative, you get 1 over 1 plus x squared, power series of that, and then integrate to get back to that tangent. This is the power series as long as x is between -1 and 1. So -1 to the n times x to the 2n plus 1 over 2n plus 1. So if you have this function, then we have that r tangent of x equals the sum from 0 to infinity, -1 to the n times x to the 2n plus 1 over 2n plus 1, okay? It's handy here. And just to get a feeling of what this is, notice that the only terms that survive here are the odd powers, okay? Odd powers of x. The even powers, they disappear, so the coefficients are 0. So we start with positive, so this is x minus x cubed over 3 plus x to the 5 over 5 minus x to the 7 over 7, and so on, okay? That's what this is, and this is valid as long as x is between -1 and 1. So we know this from before, so that means that this power series can be written in that form, okay? So this can be written as the sum from 0 to infinity of the nth derivative. Now, what is our c in this case? What is our c? 0. The center is 0. N derivative of 0 over n factorial times x to the n, okay? Now, you need to understand that the n here is the same as this n, okay? Here I'm talking about all possible n's, including even and odds. Here we're only going through the odd numbers, okay? This n is the same thing as this. So if you want, let's write this with a k, that way it doesn't, just to make it clear that those indices, they are not the same. Okay, so as an application, then now I can easily ask you find the 21st derivative of r tangent evaluated at 0. Find the 22nd derivative of r tangent evaluated at 0, and then we can easily use this to answer the question. Instead of sitting there and taking the derivative 20 times of the function r tangent, we can now use this. So find, let's see, find the 20th derivative of r tangent evaluated at 0, and then find the 21st derivative of r tangent evaluated at 0. So of course, one way would be to sit there and take the derivative 20 times, but you have to do 19 quotient rules. You don't want to do that, okay? So you want to be a little bit smarter about it, but now we know this, so we can do it. So how do we do this? The first thing that we need to do is we need to figure out what is an. We already know the series, so we need to figure out what is an, because once you know an, we can make it equal to this expression right here, and then you multiply by k factorial, and then you will get the formula for the derivative, okay? So we need an, we need the formula for an in the series r tangent. Just remember, this is the sum from 0 to infinity of -1 to the n x to the 2n plus 1 over 2n plus 1. Now, it's easier to look at it from this point of view. So remember, when I say I want an, I want this. Because this is a power series centered at 0, it's always equal to this, but now this n right here is even odd, all the numbers, because I see all the powers. Now, as you know, the only powers that survive here are the odd guys. Okay, so remember, this is x minus x cubed over 3 plus x to the 5 over 5 minus x7 over 7, etc. Okay, so we can immediately say that when n is even, an is going to be equal to 0, right? And only when n is odd, then an is going to be the coefficients, which is either 1 or -1 over 3 or 1 over 5 or -1 over 7, and so on, right? So an is equal to the following. It's going to be 0 if n is even, and then when n is odd, it's going to be equal to, let's see, it will be 1 over n for sure, right? Now we just have to figure out what happens. Sometimes it's positive, sometimes it's negative. So I'm going to put here plus or minus. How do we control this plus or minus? Well, notice that it begins with positive, then negative, then positive, then negative. So it's negative 1 to some power, right? What is this power? Well, the first odd number gives you positive. The second odd number gives you negative. The third odd number gives you positive again, and so on. So we need to have a way to index the odd numbers. We can do that easily. Notice that n equals to 0, right? So when n is odd, we can write it as 2n plus 1. Because when n is equal to 0, you get the first odd number, which is 1. When n is equal to 1, you get the second odd number, which is, let me write it as 2k plus 1. You get the second, when k is 1, you get the second odd number, which is 3, and so on, okay? So if I do negative 1 to the k, so in here, plus or minus 1 over n, I'm going to rewrite this as negative 1 to the k times 1 over n, where n equals 2k plus 1, okay? So we'll make the long story short. So a to k is going to be equal to 0, and a 2k plus 1 is going to be equal to negative 1 to the k, 1 over 2k plus 1. This is our formula. Okay, because it's a little bit complicated to write. If I want n here, then I have to say even or odd, and then in the odd case, I need to tell you that the power that you put here is not n, but it's really, what is it? N minus 1 over 2. That's the k. So instead of writing all those big formulas, it's easier to rewrite it in this form. Here I'm saying when the index is even, it's going to be 0. When the index is odd, figure out what this k is by doing minus 1 divided by 2, right? So if this is a 7, what is your k? If this is a 7, what is your k? It's 3, right? So it's pretty easy to figure out k. So find your k, and then this will be negative 1 to the k, 1 over that number. Yes? So it's easier than the previous one. And this is true for all k. 0, 1, 2, etc. Okay? So now that we have the formula, we can easily answer the question. So we know that the nth derivative evaluated at 0 over n factorial equals an. So from here it follows that the nth derivative of arctangent evaluated at 0 is going to be n factorial times an in this case. So if you have an even derivative evaluated at 0, what would this be equal to?
0.
That will be equal to 0 because you're going to put here a 2k. And if you have an odd derivative evaluated at 0, what do we get? 2k plus 1 factorial times negative 1 to the k, 1 over 2k plus 1, right? And just plugging in into this formula. When you put 2k plus 1 here, you're putting 2k plus 1 here, but a 2k plus 1 is this expression here. So we can rewrite this a little bit nicer. We can write this as negative 1 to the k times 2k factorial, right? Because this 2k plus 1 cancels with the 2k plus 1 from here, and then you're left with the previous factorial, which is 2k factorial. So this is our formula for any derivative of arctangent. So in particular, what do we want? The 20th derivative of arctangent evaluated at 0. So what is this? 0, right? Because it's even. Now what do we want? The 21st derivative of arctangent evaluated at 0. What is this? That will be negative 1 to the 21. Well, not 21, but so we need to write 21 as 2k plus 1. So k will be 21 minus 1 over 2, so that's 5. No, that's 10. So that's 20 minus 2. So that's negative 1 to the 10, and then 2k that will be 20 times 20 factorial. So 20 factorial. That's the 21st derivative of our time. Okay, questions on this example? So this is just one little application that you can use, the point is that you can use this power series expansion now to find derivative of any order of the function. If you have a function and you know this power series expansion, you can find whatever derivative you want, okay? Or whatever order you want. Evaluate it at the given center, okay? You need to know this function at a given center, then you know all derivative at that center. Yes, question? Any questions? I mean, the whole point is that if you know the series, remember that we did an example like 2 lectures ago in which I gave you a series and then, we figured out an. And sometimes it could be a little bit complicated because if you don't have all the coefficients in the series, then your an is not what you see here. You cannot tell me that an is negative 1 to the n over 2n plus 1. It's not as easy as that. Because here you're only looking at odd numbers, but an, when we say an for the power series, we want everything. We want the coefficients of the even and the odd powers as well. Okay? And so you need to study what happens in this case. And first you realize there is no even powers, therefore that means the coefficients are 0. Okay? That's easy. But now the odd powers, the sign is alternating, so we need to control that somehow. And the idea is that the first odd power, which is 1, is positive, and the negative, positive, negative, so you basically need to index the odd numbers, okay? And one way to index the odd numbers is like this. How you write an odd number, and then k tells you the position of the odd number. When k is 0, you get the first odd number. When k is 1, you get the second odd number, and so on, okay? So that's why we do negative 1 to the k. That's it. Questions? Okay, so again, this is, yes.
So if we scroll up just a little bit more. Okay, so if we plugged, let's say we plugged 2 in for k in a2k plus 1, that would then give us the 5th term of the series.
Yes.
Okay.
A5, the 5th coefficient.
Right. So by plugging in 2 for k, we get the 5th term of the series, so a5, but we plug in 2 for k and the negative 1 to the k and the 1 over 2k plus 1, which gives 5, which is, okay.
That's just a formula.
Okay.
But that's not what you do. What you do is you know this number and you need to find k. Remember, when you have the series, like what we did here, you have the series, you want to figure out the 21st derivative, for example, right? So n is 21.
Right.
So that means 2k plus 1 is 21.
Right.
So you have to find your k.
Okay.
So this happens when k is 10.
Okay.
Right? And that's what you use in the formula.
Okay. Okay, I see.
So typically you don't plug in k here. You know this and then you use that to find your k and then you use it in the formula. Okay? Yes? All right. So that was an example on an application, if you will, on how to use this knowledge of the coefficients of the power series to compute the derivative of any order. Okay? As long as you know the power series. But now we can use this idea to find power series of other functions. Because remember, we did this exercise because we knew already the power series of our tangent that we found it by other means. Okay? We didn't have to take a bunch of derivatives, nothing like that. But what if you have a function and you want to come up with a power series for that function, but you cannot play the tricks that we did before, taking derivative or integrating and using geometric series. Okay? That's what we did last time, using geometric series all the time. Well, in that case, this right here would be a recipe to be able to figure out the power series. But the problem is that then you have to be able to control derivative of any order of that function, and you need to have a formula for that. Okay? In general, that's not easy to do, but there are some functions like sine, cosine, e to the x, that's easy to do. Okay? So we're going to get for free some power series representations for those functions. So that's what I'm about to define. So given a function, so definition. So this is the definition of Taylor and McLauring series. So if you have a function that can be differentiated as many times as you want, that is infinitely many times differential. So if a function f has derivative of all orders, at x equals c. So what I mean is that you can take the derivative, whatever derivative you want of the function, and then evaluate it as c, and it's defined. So those derivatives are defined as c. Okay, at x equals c, then the series. So because you can take as many derivatives as you want, you can always define this series. Nth derivative evaluated as c over n factorial times x minus c to the n from 0 to infinity. And remember what this is. This is just, so when n is equal to 0, this is just the value of the function as c. When n is equal to 1, this is f prime evaluated as c times x minus c. Myself some space. And then when n is equal to 2, this is the second derivative of letter c over 2 factorial times x minus c squared, and so on. Okay? That's what this is. So this is just a number, the value of the function as c, then x minus c squared, etc. And the coefficients are given by the derivative of letter c divided by the corresponding factorial. Okay? Same power factorial. So then this series is called the Taylor series. It's called Taylor series of f of x at c. Okay. So notice that I didn't write that f of x equals this series. Okay. You have your function, and then given this function, we can write down the series. It has a name. Okay. Now we want to see what's the relationship between that function and this series. Okay. In most cases, it will turn out that this function will equal the series. Okay. But it doesn't have to be. Just keep that in mind. So we call this the Taylor series as C, and then when the center, notice that C here is whatever number you want, as long as this makes sense, that you can find this expression. But if C equals 0, this is called the Taylor series at 0, but it's also known as the McLauring series. So when you see McLauring series, that's just Taylor series with center 0. Okay? So if C is equal to 0, then it is also called McLauring series of F. Okay? So, for example, what you see in this table, this is a table of all the Taylor series centered at 0, or the McLauring series of these functions that you see here. Okay? As I mentioned, we already know 3. Now, since we already know these things, let's figure out the Taylor series or McLauring series for exponential, sine, and cosine. Okay? So let's find those. All right. So let's see. Before I do that, let me actually, yeah, this is a good place to do it. So example. Find the McLauring series of f of x equals sine. Then once we do sine in detail, then we're going to be able to easily do cosine. And then e to the x, of course, is pretty easy to find. Okay, but let's do the sine. So solution. So number 1, so we have f of x equals sine of x. So we know that the McLauring series is given by the sum from 0 to infinity of the nth derivative evaluated as 0 over n factorial times x to the n. So really the question is, the only thing that we don't know at this point is what is this guy, okay? Once we figure this out, then we're good to go. So let's run some experiments. Let's start taking some derivative for the sine function and see what happens, okay? And evaluating as 0. So let's see, when n is equal to 0, we have just the value of the function, right? So remember, n equals 0, let me put here, n equals 0, that's just f of x, which is the function sine. So if we evaluate that at the center, what do we get? What's sine of 0? That's 0. When n is equal to 1, then you have the derivative of the function that's equal to cosine. So when you evaluate the derivative of the center, we get cosine of 0, which is 1. When n is equal to 2, you get the second derivative, which is negative sine. And then when you evaluate this as 0, what do we get? 0 again. Now when n is equal to 3, we get the third derivative is negative cosine. And when you evaluate this as 0, we get negative 1. Now when we do n equals 4, so when we take the fourth derivative, what do we get? This is the sine function. So the fourth derivative of 0 is equal to 1. So if we take a look at what's going on here, notice that we actually went back to the beginning, right? So the fourth derivative is actually the same as what we started. So if we keep on taking derivative, what we're going to do now is we're going to start cycling through the same functions again, right? So the fifth derivative would be cosine, then negative sine, then negative cosine, then back to sine, and repeat over and over again. Yes?
Why is
Why is sine 1?
I don't know.
The fourth
Is
derivative.
it? You mean this one, right? So the point is that now this is the same as this, okay? So now the cycle is gonna repeat itself. So every time that we hit, let's say every fourth derivative, so a multiple of 4, we're gonna be getting sine all the time, yes? And then every time that we get something of the form, a multiple of 4 plus 1, or 4k plus 1, we're gonna get cosine, then we get negative sine, 4k plus 2, 4k plus 3, we get negative cosine. Which on this side means that we're gonna be getting 0, 1, 0, negative 1. So the zeros are obtained every time the derivative is even, if you notice. And then the 1 or negative 1 are obtained whenever you have an odd derivative. The positive 1 is when it has a form 4k plus 1. The negative 1 is when it has a form 4k plus 2. Okay? So let me write that down. So now the values, so the expression repeats itself. So now the values begin to repeat themselves. So the moral of the story is the following. So we see that every time that the derivative is, if you have an even power, right? So the even power, we know that this is going to be plus or minus sine. If you want to be more specific, every time that the power is a multiple of 4, it's going to be positive sine. If it is of the form 4k plus 2, so the remainder is 2 when divided by 4, then it's going to be the negative sign. But what I care about is a 0, and the 0 is going to be equal to 0. Okay, so I'm not going to pay too much attention to the function itself. From here, it follows that when you plug in 0, we get 0. Okay, so we are not going to have even powers in the McLauring series expansion for the sine function. Now, for the odd case, we already have practice on this from a previous example with arctangent, so we're going to be able to do it nicely. So f2 to 5 plus 1, when it's an odd number, then we know that this is going to be plus or minus cosine, which is telling me then that this is going to be plus or minus 1. Now we just need to spot when is it plus, when is it minus, okay? So it's not enough to just say odd numbers. So it turns out that this is exactly the same situation as before. So when n is equal to 1, you get a plus. When n is equal to 3, you get a minus. So then when n is equal to 5, we're going to get a plus again, and so on. So once again, we are cycling through the odd numbers, and we start with positive, negative, positive, negative. So this is, what is this? How can we write this? Negative 1 to what power? To the k. This is exactly the same situation as we did with the arc triangle. We are cycling through the odd numbers, so this k here is the one that's telling you whether you should use a positive or a negative. Okay? When k is 0, you're talking about the first odd number, so as positive. When k is 1, you're talking about the second odd number, so as negative, and so on. This is exactly what we see here. So, the McLauring series of f of x equals sine is the sum from 0 to infinity. Now remember, the even guys are not there, so this is going to be negative 1 to the n, and then that's x to the 2n plus 1 over 2n plus 1 factorial. Remember, the even ones are not there because the coefficient is equal to 0. Okay, so the only coefficient that survive are the 2k plus 1, and those are equal to negative 1 to the k, which in this case I'm calling it n, okay? And you have x to the 2n plus 1, right? So that's the odd power, and then this is the n factorial in the formula, which in this case is only the odd guy, so that's why it's 2n plus 1, okay? So in other words, and this is equal to x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial, and so on. Okay? So, only odd powers, and the easy way to remember this is that sine is an odd function. Okay? And that's why you only have your odd powers. Okay? And you have to alternate. All right. Questions? Okay, here I'm gonna give you a little homework for you to do, and it's to check the following claim that I'm gonna make. The interval of convergence, now you know how to find interval of convergence of this, is all real numbers. Okay, so this series converges for all real numbers. You can do this pretty easily by using the ratio test, as we did last time. Okay, questions about how we found McLaurin series for the sine function? Okay, if we now want to find it for the cosine, notice that there is no need to do this whole work again. In general, if you're given a function and you are asked to find McLaurin series, this is what you need to do. You need to start taking derivative and try to see what happens with this derivative over at 0, how it looks like. But the cosine, instead of repeating the same work, notice that it's actually the same situation, it's just that instead of beginning here, we start here, right? And then when you start taking derivative, then again, we have our first 4 derivative, right? So the 0th derivative, the first, the second, the third. The moment that you take the 4th derivative, we're back to the beginning, right? So it's exactly the same thing as this guy, it's just that everything is shifted down, okay? So this is the function, so we begin at the even case, so at the 0th, the second derivative, etc., we're gonna get 1, negative 1, 1, negative 1, and then 0 at the odd derivatives, okay? So that's why I said once you do sine, cosine, we get it for free, basically. So for the cosine function, so similar to above, we can easily show that when the derivative is even, then you're gonna have either a plus or minus 1, right? You get plus or minus 1, which in this case, the k is the one that's gonna tell you what is it. The first even number will be positive, the second even number is negative, and so on. And then the odd derivative is going to be 0. So that means that we're going to be missing all the odd powers in the power series expansion. We're only going to have the evens. So McLaurin series of cosine is sum from 0 to infinity, negative 1 to the n. So this time we have x to the 2n over 2n factorial. because again, the odd guys, they are equal to 0, the coefficient. So it will be 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial. So, okay. And once again, just like before, the interval of convergence here is from negative infinity to positive infinity. You can check that easily by doing your ratio test. Okay, questions for this? All right, so how about e to the x? Let's see, that one is super easy. That one we don't need. So if we have e to the x, who can tell me? What's the general formula for McLauring?
It's x dot n over n factorial.
So McLauring would be the sum from 0 to the n, from 0 to infinity. What's the formula for McLauring? Not the end result, the formula. What is it? N derivative of the function evaluated as 0 over n factorial times x to the n, right? But what do we know about the derivative of e to the x? Regardless of the power, it's just e to the x, right? So that's just e to the 0 over n factorial times x to the n, but e to the 0 is equal to 1. So we get x to the n over n factorial. Yes? All right, and once again, the interval of convergence here, we did this last time, is all real numbers, from negative infinity to positive infinity. Okay, questions?
So just to make sure, the 0 is there because it's the center, right? C minus C.
All right. Remember, the word McLaurin means Taylor series with center 0.
Oh, okay.
So if you look at the definition, we have Taylor series centered at C, but when the center happens to be 0, we call it McLaurin. It's just Taylor series, but the center is 0. So what you evaluate in the formula, what you evaluate when you take the nth derivative, when you evaluate the nth derivative, you have to do it at the center. Okay? Whatever you have here, that's what you evaluate it at. Okay?
Question.
Yes.
So are there power series that can't be differentiated like an infinite amount of times? So that, so meaning, are there power series that aren't either McLaurin or Taylor series?
No, so if you start with a power series, it's always this form. That's what we just proved.
Okay.
The point is that there are
Power series.
functions.
Okay.
There are functions that cannot be differentiated as many times as you want.
Okay.
Okay?
Okay.
And then for those functions, you won't be able to play this game.
Okay.
But if you have a function that you can take as many derivatives as you want, that's infinitely many times differentiable, then you can do this, and there will be a McLaurin and or Taylor series.
And how do we determine
Okay.
if a function can be infinitely differentiable?
Well, that's one question. That depends on the function that you're given, right? To see if a function is, I mean, typically, if the function is made out of, as you can see, the elementary functions, they can all be differentiated as many times as you want. Sine, cosine, e to the x, polynomial functions. Well, polynomial functions, eventually they become 0 anyways. Rational functions, you can take as many derivatives as you want, right? But for example, you have to be careful, like 1 over x. 1 over x is differentiable as many times as you want, but you have to stay away from 0. So you are not going to find a McLaurin series for 1 over x, right? You will find a Taylor series at another center, but not at 0, because 1 over x is not even defined, right? So as long as your function is made out of elementary functions, you will be okay. But you may have weird functions like piecewise defined, and other type of functions that are not differentiable at certain points. And then in that case, you cannot do this. But the functions that you normally will come across in problems, in reality, in real life, you don't come across nice functions like this. You come across piecewise functions that in pieces, they could be modeled or approximated by stuff like this. But the function itself may not be good at all. Okay? That's a different story. That's something you will learn later when you are more advanced engineers. You will learn how to deal with those cases. Okay? But as long as you can take as many derivatives as you want of the function, you can always do this. And by looking at the formula, like e to the x. If I take derivative, I always get e to the x. Right? And so
Just memorize the formula for that, or work it out and you
Yeah, but in practice, you should know, you see this table that I gave you here? So let's see, from the table, what do we have so far? So in this table, so we already know these things from before. If you forget them, then you should know the trick to get them, which is take derivative, use power series, use a geometric series, and then integrate to get them back, right? Now we discuss this one, and this one. Of course, you can sit down and recover them every time because, as you saw, it's really not that hard. But it's kind of convenient to know them because when you have a problem, you don't want to derive the series and then use it. You want to just recall it, use it, and good to go. Okay. So this is the last one. This is the other one that we need to discuss. But before we get there, let us talk about something very important. So far, for example, I said the McLauring series of the sine function is this guy. The McLauring series of e to the x is this one over here. But are they equal as functions? This is a function that's defined over all real numbers. This is a function that's defined over all real numbers. But do they equal to e to the x? Is this equal to sine of x? When we say that, what I mean is that this function converges to this one. That this function converges to this one. Okay? So for example, if you put an e squared here, and if you put a 2 here, that's a series 2 to the n over n factorial equals e squared. That's what we want to figure out. Okay? So let's give an answer to that question. And the answer is that yes, for all of these guys, the series equals the function, but we need to formalize it. Okay? And basically, the idea is that, remember, to ask for convergence of this series is to ask for the limit of the sequence of partial sum. When you look at the sequence of partial sum of this power series, that's called a Taylor polynomial. You have a bunch of homework problems about Taylor polynomials. And you can approximate Taylor polynomials. The functions, you can approximate them always with Taylor polynomials. A theorem, which is a little bit hard to prove, but you actually have the knowledge because it uses Roll's theorem from calculus 1 of Taylor, that's why these are called Taylor series, says that when you approximate a series by such a polynomial, a function by such a polynomial, a Taylor polynomial, there is an error, and Taylor gives us a formula to bound that error. And that's why we can then figure out whether this converges to the function or not, because we just take the limit of that error. If the limit is 0, then the function equals the series. I'm going to write what I just said. Okay? But that's the idea. So anyways, now we know Taylor series. So the Taylor polynomial is pretty easy to understand now. It's just a sequence of partial sum of the Taylor series. Okay? So instead of being at infinity, just cut it at n. And that's your Taylor polynomial. So let me write that down. Again, we're trying to address a question, does the series equals the function that we are finding? Okay? We are given a function, you come up with a series using this Taylor series. Now, do they equal each other? Let's answer that question. So, definition, Taylor or McLauring polynomial. So, a McLauring polynomial is just Taylor with center at 0. Okay? So let f be a function. Now, this idea of Taylor and McLauring polynomials, we always talk about the series first because then I just have to tell you the sequence of partial sum is what we call Taylor polynomial. But for every function, you can always find a Taylor polynomial because you don't have to have a function that is differentiable infinitely many times. You only have to be able to differentiate it up to the degree of the polynomial. So n times. That's all you need. Okay? So let f be a function with n derivative. So with derivatives of order n. Okay? Or let me say at least n. Meaning that, if you have more, that's fine. Of at least n at x equals c. So you can take at least n derivative of the function, and they are all defined at the point x equals c. That's what I mean with that sentence. Okay. Then there's a polynomial that we can define, and this polynomial is exactly the same as. So we're gonna call it Tn of x. If you read the book, they call it Pn, but in the homework they call Tn, and I like T more, Taylor, right? But if you read the book, you will see P instead of T. So then the polynomial Tn of x, this is exactly the same thing as the Taylor series formula. It's just that we're going to begin at 0 and stop at n instead of going to infinity. But then it's the same thing. C over k factorial times x minus c to the k. So basically, Tn is going to be this. It's going to be the value of the function at c plus the derivative of the function at c times x minus c plus the second derivative at c over 2 factorial times x minus c squared, and keep going all the way up to the nth derivative evaluated at c over n factorial times x minus c to the n. So notice that this is a polynomial of degree n. So that's why we write Tn here. So this is a polynomial of degree n. This is a polynomial, not a series, it's a polynomial. Moreover, how many terms does it have? How many terms are here? N plus 1. Because this is the constant term. You see, remember, start counting at 0. 0, 1, 2, 3, all the way up to n, there are n plus 1 terms. Okay? So this is called, it's a polynomial, and we call it the Taylor polynomial, the nth Taylor polynomial for f at c. It's called the nth Taylor polynomial, and for f at c. Okay? So if c is equal to 0, as usual, then it is called the nth McLauring polynomial. For f. Okay? So again, whenever you see the word McLauring, that just means Taylor with c equals 0. Okay? That's the easier way to remember. Okay, so now, why is it so? Notice that this you can do it for any function as long as you can take as many derivatives as the degree of the polynomial. So if I ask you find the fifth Taylor polynomial of a given function, I'm telling you n is equal to 5, so you have to play this game up to 5. Okay? So you need to give me 6 terms. You understand this? The constant plus the first derivative, second derivative, all the way up to the fifth derivative. Okay? So, and then the remark here is that the nth Taylor polynomial is just the sequence of partial sum of the Taylor series. Okay? So for a Taylor series, if you have a Taylor series of a function, so remember this is equal to the sum from 0 to infinity, fn at c over n factorial x minus c to the n. So for this Taylor series, a sequence of partial sum Sn is actually the nth Taylor polynomial. Okay? So Taylor series and Taylor polynomials, of course, they are related because the Taylor series converges as long as the limit of the Taylor polynomial as n approaches infinity converges, right? Because that's how we define convergence of a series. If the limit of the sequence of partial sum converges. So let me give you Taylor's theorem, which is, if you want, is the most important theorem in this chapter, and is the one that tells you that then every function can be approximated by its Taylor polynomial, and the approximation will leave an error, of course, and there is a specific formula for that error. Okay, so be able to control that. Yes.
Why does it say f to the nth derivative times c? If it's
Of
c,
c.
wouldn't it be?
What do you mean times c?
Oh wait, it's of c. You're right. Sorry, I forgot that. Dumb question.
Okay. So basically, what I'm about to tell you is that every function can be approximated by polynomials, and this is in practice what happens. Okay, because polynomials are very easy to handle, and they are very nice. They're continuous functions. So when you have a function that's super complicated, what you do is you approximate the function with polynomials. The question is, what should the degree of the polynomial be? Is it okay to do it with a linear, with a line? If you are interested around in a very small interval around a point, you can look at the tangent line and then you do linear approximation. You learn that in calculus 1. But what if you want a better approximation than that, or something better than that, or if you want to move away from the point? then maybe a line is not okay. How about with the parabola? Can you approximate your function with a parabola or with a cubic? So in general, we want to approximate functions with a polynomial. The question is, what should be the degree of our polynomial? Taylor's theorem allows us to figure that out, okay? Because when you approximate with a Taylor polynomial, there will be an error left over, and we're going to have a specific formula that will allow you to bound that error, if you know something about the function, of course. So let me write that down. So let me write Taylor's theorem, and I'm going to try to put it in words that are easier to understand. Let's see, Taylor's theorem. So here is the condition. So if you want to approximate a function by its Taylor polynomial, we need the function to be, we only need n derivative, but if you want to bound the error, we need the function to be n plus 1 times differential. So you have to be able to take one more derivative, okay? So suppose f is a function that can be differentiated at least n plus 1 times at the point x equals c, or I would say on an interval, so one time on an interval, on an open interval containing c. On an open interval I, I'm calling it I, containing c. So we assume that. Then let Tn of x, remember what this is. This is f of c plus f prime of c times x minus c. Second derivative. It's good to write it down several times until you get a feeling of what this is. So let Tn be the nth Taylor polynomial. Be the nth Taylor polynomial at C, and let Rn be equal to f of x minus Tn. So basically, here's what I'm doing. So we have a function that you can take as many derivatives as you want. Now, at least n plus 1 times derivative. Then let Tn be the nth Taylor polynomial. Notice that you can do at least n plus 1. So n is 1 less than n plus 1. Okay. The Taylor polynomial. Here, what am I doing? I have my function. I have the Taylor polynomial, and I'm looking at the difference. Okay. We're calling this Rn. So this right here actually represents the approximation of f by Tn, right? Because this is the error. So let Rn be the error in approximating f of x by the nth Taylor polynomial. So with this, then we can say the following. Then Rn of x, actually, then here's a statement. For every x, this is a little bit technical. I will try to explain what this means. So for every x, there is a z between x and c such that Rn of x is going to be equal to the n plus first derivative of the function evaluated at this mysterious z over n plus 1 factorial times x minus c to the n plus 1. So this is the Lagrange version of Taylor's remainder, but this formula is it's very useful to use. Now, let me explain what I'm saying here. So I'm telling you that there is a way to figure out what is the error in this approximation by using this formula, but you need to understand that this z, the way this is written, this z depends on this x. If you change x, then z may change. Okay? All we know is that this z is a number that is between x and c. Okay? So you have to be very careful when you work with this, because you need to understand that for every x, there is a z. So if I change this number, this one potentially changes. So this depends on x. Okay? So you write that down here. So z depends on x. Okay, so this is what Taylor's theorem says. Okay, and again, the proof of this is you have the knowledge to understand it, but it's a little bit long, and I think it's not worth discussing it. But it's in the book, and you can see it. You will be able to understand it if you go through it and if you pay attention to the details. The heart of the proof is to use Rolle's theorem, which is something that you learned back in Calculus 1. That basically says if you have a continuous function and the function at the endpoints of an interval has the same value, then there has to be a point in between for which the derivative is 0. And this is something that graphically makes sense. So the idea here is to use Rolle's theorem. If you have a function, let's say that here is a, here is b, and you have a function for which g of a equals g of b, and it's continuous, g continuous. So I don't know, g is continuous on the interval ab. Let's say it does something like this. Okay, the function can do whatever it wants, but it has to be in a nice continuous way. And then if that happens, that is continuous and differentiable on the interval ab, and f of a equals f of b, then there has to be at least one point in between for which the derivative is equal to 0. So there has to be a point at which there is a horizontal tangent line. So here, the derivative of the function, I'm calling the function g, is equal to 0. That's what Rolle's theorem says. Okay? And the idea is that here you build a function that you call g. It looks complicated using f and the Taylor polynomial. And then that function, because it looks like a polynomial, it will be continuous. You apply Rolle's theorem to it. And this c that shows up is this z that you see here. Let me call it z. That way. Okay? So that's the basic idea of the theorem. This is Rolle's theorem. So continuous and differentiable. Then there is a z between a and b such that g prime of z equals 0. This is Rolle's theorem. For example, the mean value theorem is an application of Rolle's theorem in a particular case. Okay, so Rolle's theorem is very important. And mean value theorem was used to prove fundamental theorem of calculus. So if you want, Rolle's theorem is the one that gives you fundamental theorem of calculus. So this theorem that you learned back in Cal 1 is fundamental for all these things. Okay, so what Taylor's theorem is telling us here is that when you approximate a function, okay, when you approximate a function by a polynomial, there is an error, okay, which is different, and that error has this form, okay. So now the question is, can you bound this error? This is useful as long as you can bound. It really depends on the function. If the function itself can be bound, then this takes a special form. So let me write here a corollary of this. So corollary. So the first thing is, number one, if the n plus first derivative of the function is bounded, and if you can bound this for all x in the interval I, in other words, because remember, this z changes when x changes, but z is always between x and c anyways. So z is also a point inside that interval. So if this derivative is bounded for all x in I, so what that means is that the absolute value of this is going to be less than or equal than m for some n. That's what it means to be bounded. for some m, then we have the following. We have the absolute value of the error, which equals the absolute value of this over n plus 1 factorial. So then this is going to be less than or equal than m over n plus 1 factorial times x minus c to the n plus 1. Okay? So now what we just did here is that if you can bound the n plus first derivative of the function, then that means that we can remove this z out of the equation. Okay? And then the error is bounded by this expression right here. And if moreover you know what the interval is that you care about, you will be able to also bound this part, because you can find either whatever is the maximum value of the interval, let's say the radius of the interval. In the case of radius of convergence, you can replace this by r, which is the radius of convergence. Okay, and then you have a bound that does not depend on x at all, so it's a uniform bound, and then you're going to be able to figure out exactly what the error is. Okay, or an upper bound for the error, which is at the end all we care about. So the important thing of this remark is that this does not depend on z. You see, this z here is problematic. You see here is troublesome because we don't know what it is. It's something between x and c, but we don't know what it is. Okay? But if you can bound the n plus first derivative, then for example, the cosine function, we can always do this because this is always less than 1, right? Because the n plus first derivative of sine and cosine is a plus or minus sine or a plus or minus cosine. In any way, in natural value less than 1, so we'll be able to nicely bound that. So that's the first remark. The second remark is that because Rn, we can always do this, and Rn is a result of approximating the function, the Taylor polynomial by f of x, then if the limit of Rn is equal to 0, what does that mean? That means that f of x minus the limit, because this is a constant with respect to the limit, as n approaches infinity, then f of x minus this limit is going to be equal to 0, right? So the f of x equals the limit of the Taylor polynomial. But what's the limit of the Taylor polynomial? The Taylor series, because this is the n sequence of partial sum. And the limit equals the value of the series. So, in other words, if the remainder equals 0 when you take the limit, then the function converges, or the series converges to the function. So we can say the function equals the series. Okay? So that's the second consequence here. So let's write that down. The Taylor series sum from 0 to infinity of x minus c to the n. So this converges to the function itself if and only if the limit as n approaches infinity of Rn equals 0. Okay? So, an exercise is to now go to the list of McLauring series that we have. We have to construct the remainder, the Taylor's remainder, take the limit, and show that the limit is 0, and then we'll be able to say that sine equals the series. E to the x equals the series. I'm going to do it for one of them. Okay? So, for example, let's look at f of x equals sine of x. So we know the McLauring series. So the McLauring series is the sum from 0 to infinity, -1 to the n. Remember, sine is odd, so only the odd terms survive. That's the easy way to remember. Cosine is even, only the even terms survive. Okay? So that's the McLauring series. Let's construct Rn. So the remainder, so Taylor's remainder Rn of x equals n plus first derivative as z over n plus 1 factorial times x to the n plus 1. Remember here our c, our center is 0. Okay? Taylor remainder is this guy for c between x and 0. Okay? Because remember, our c here is 0, or z between x and 0. So, so we have this. Now, the remark here is to notice that whatever derivative you're taking for the sine function, in particular the n plus first derivative, if you remember the computations that we did, this is going to be either a plus or minus sine or a plus or minus cosine. You remember the exercise that we did, right? The derivative that we're cycling through one of these 4 functions. And why do I write like this? Because it depends on what is this guy. Is it a multiple of 4, or remainder 1, 2, or 3? Okay? The point is that regardless of what it is, we can always say that the absolute value is going to be less than or equal than 1, right? So these are m in the remark. So you can take this as our m in the remark. So the absolute value of the remainder is going to be less than or equal than 1 over n plus 1 factorial times x to the n plus 1. Yes? And what happens to this when n approaches infinity? If we take the limit as n approaches infinity, what happens here? Remember, this is a variable, but whenever we take this limit, x is fixed, right? Because it's with respect of n. Here we have a power, in the bottom we have exponential. What grows faster? Factorial. I said exponential. In the bottom we have factorial, right? So we have a power here, we have factorial, so the bottom grows faster. So this limit is 0 for all x. Now, if the absolute value of Rn goes to 0, then Rn itself goes to 0, right? So limit as n approaches infinity of Rn itself is equal to 0 as well, right? So we can say now that sine of x actually equals this series. And this happens, this is true for all x. Okay? In the case of cosine, it's exactly the same story, because the error, that would be,
It just beats
so then, it's just that you have 2 to the n over factorial, right? So when you do this, what is it? So you have the cosine function, so the derivative of the cosine function is once again plus or minus sine or a cosine. So it's going to be bounded by 1. So when you take the limit, the same thing is going to happen. Yes? That's very easy to see. Okay, so similarly, you can show the cosine, so the McLauring series for cosine converges to itself. That's 2n for all x. And then, for e to the x, let's do it for e to the x. And then for f of x equals e to the x, we have the McLauring. It was a sum from 0 to infinity of x to the n over n factorial, right? So what's the error here? So remember, this is the n plus first derivative evaluated as z over n plus 1 factorial times x to the n plus 1. And this is for z between x and 0. Okay? Now, the n plus first derivative of e to the x is just e to the x. So this is e to the z over n plus 1 factorial times x to the n plus 1. So if we take absolute value, that's positive, so the absolute value is just here. Now, if you take the limit of this as n approaches infinity, what's going to happen? Remember, z depends on x. You don't know what z is, but the moment that you fix x, z is also fixed. Okay? And here in this limit, when you take the limit, x and z, they are both fixed. The only thing that's changing here is n. Once again, this is just a number, right? The top is a power, the bottom is a factorial. factorial wins over. So this is gonna be 0 for all x and z anyways. Okay? So once again, e to the x equals is McLauring series. And this is true for all x. Okay? So every time that you need it, you can now, when you have the function sine, cosine, e to the x, if you want, you can replace them by this power series, by this McLaurin series, and then work with them. For example, as an application, I'm gonna leave this to you, but then now you can compute something like this: the integral from 0 to 1 of e to the negative x squared with error, let's say less than 0.0 with 3 decimal places accuracy. Now you can do this. Why? This integral itself is something that you cannot compute by elementary means. You cannot do e to the negative x squared. You can try as much as you can. There's no substitution. Nothing that you can do is going to work. But now you can write this as a power series. It's going to be, and you know we can integrate power series very easily. It's going to be alternating, so you can easily now bound the error using the error bound for alternating series. So let me just show you how this is done here. So you have e to a negative x squared, and then what we can do is we can replace e to the x by its power series. Now, of course, this is a composition of e to the x with a function negative x squared, so that just means that I plug in negative x squared in here. Okay. So that would be the sum from 0 to infinity of negative x squared to the n over n factorial. Let's rewrite this. So that would be negative 1 to the n times x to the 2n over n factorial. Then passing the integral through, we get the sum from 0 to infinity, negative 1 to the n over n factorial. And then we integrate x to the 2n. What do we get? 2n plus 1 over 2n plus 1.
10.
And we need to plug in from 0 to 1, right? The limits of integration. So what is this? So that would be the sum from 0 to infinity. So when you plug in 1, you just get 1. So that's negative 1 to the n over 2n plus 1 times n factorial. Because when you plug in 0, you're going to get 0. Because all these x's, they survive even when n is 0, because this is 2n plus 1. So the integral from 0 to 1 of e to a negative x squared dx equals this power series. Okay? We know that this converges by alternating series test, right? So this converges by the alternating series test. And now you can figure that you can find how many times you need to get an error less than 0.001 by using the alternating series remainder theorem that we discussed earlier. Or if you want, you can use Taylor's theorem, but it's easy to use alternating remainder theorem here. So for example, what do we want? The an plus 1. So we want Rn, which is less than or equal than an plus 1. And we want this to be less than 0.0001. So an plus 1 is going to be the positive version. So that's 1 over, if you put n plus 1 here, you're going to get 2n plus 3 times n plus 1 factorial. You want this to be less than 0.001. And now it's just a matter of trying things. So let's see. Okay, I'm going to start with n equals maybe 3. So if we put n equals 3, what do we get? We get 6 plus 3,
9.
That's 9 times 4 factorial. Then you flip it. Okay, I get, this is going to give me 0.0046. Not good. So if we put 4, it's going to be 8 plus 3, 11. So 11 times 5 factorial. Then flip it. Okay, I get 0.00. I already have my 3 zeros, but then I have a 7 here. So I'm gonna keep going one more, and that's gonna do the trick. So if n is equal to 5, then the an plus 1 term, remember what I'm getting here is an plus 1. Okay, my a6 would be, n is 5, I get 13 times 6 factorial, flip it. Okay, and we get 0.123. Let's see, I get 1, then I get 0, 6. Slightly, so I have to go one more.
Wow, they just,
So then, one more. So 7, that's 14, plus 3, 17. So 17 times a factorial. Flip it. Now it goes 0.1, 2, 3, 4, 5. And this is what we need. So that means that we stop right here.
so you find.
N equals 6. Okay? So you have to use up to n equals 6 because the first term that you neglect is a7, and that's less than 0.0001. Okay? So that's less than. So you're gonna go up to n equals 6. So you can approximate this by a0 plus a1 all the way up to a6. Okay? All right. Questions? So this last part, you're already familiar with that. This is just a little, application that now every time that you have a series, an integral, if you have a function that you cannot compute the integral, you can view that function as a series. You need to be able to find Taylor series, etc. But then the point is that you can easily integrate power series. Okay, so you can always do that. And then the question is, can you approximate it? If it's alternating, then you have alternating series test, which is pretty easy to use. If it's not alternating, you can try Taylor's theorem. Okay. Okay. Questions? Yes.
Is the homework for this still due tonight, or is that getting moved?
I changed it to Tuesday.
Okay.
Before coming here. Why will it be due tonight? I know it was
Just
due
making
tonight.
sure.
You should know by now that things get moved eventually.
It's more exciting that way.
So, let's see, I have 2 minutes. It's just that I want you to understand what this is. Look, this one. Do you know what this is for the binomial theorem, for the binomial series? Because otherwise, if you have, for example, the square root of 1 plus x, you're not going to be able, if you don't know what this is, and then if I ask you to find the Taylor series or the McLauring series of square root of 1 plus x, you're not going to be able to do it. Because that would be the case here for r equals 1/2. So for example, if r is 1/2, then that means square root of 1 plus x, you can write as the sum from 0 to infinity of 1/2 choose n x to the n. Now, the question is, what is this? When you have an integer here, if r is an integer, we know exactly what it means, okay? This comes from combinatorics, but this is just the following. So, definition, r choose 0, we define this to be 1. This is always equal to 1, okay? Now, if you have, then r choose 1 is going to be equal to r, okay? And now for n greater than or equal than 2, how do we define r choose n? We define as follows. This is r times r minus 1 times r minus 2, all the way up to 1 less than n. So that's r minus n plus 1 over n factorial. Okay? That's how we define that. And, if you give me a second, you will be able to see why this is the case. It's pretty easy to see why we're making that definition. And that's because we are interested in this function. If you have the function 1 plus x to the r, the question is, what's the McLauring series? Okay? And as you know, we need to analyze the derivative of this. So what's the derivative of the function? So f of x is the function itself. So that means the seat of derivative at 0 is just 1, right? Now, what's the derivative of the function? It's r times 1 plus x to the r minus 1. So what's the first derivative of 0? Just r, when you plug in 0. What's the second derivative? R times r minus 1 times 1 plus x r minus 2. So second derivative of 0 is r times r minus 1. So basically, this guy is gone. When you plug in 0, that becomes 1. Okay? So if you see what happens, every time that you take derivative, you're going to have the product from r all the way down to r minus 1 less than this guy. Okay? Or I guess 1 more than this guy, if you want. Because this will be plus 1, right? R minus 2 plus 1 is what give you r minus 1. So if you keep on going this way, you should see that the nth derivative of the function is what? Is r minus 1, r minus 2. That will be the next one, right? All the way up to r minus, now will be r minus n, but we need to do plus 1. So you stop here. This is minus 1, that you get it by looking at this power and doing plus 1. Okay? Times 1 plus x to the r minus n plus 1 to the r minus n. So the nth derivative of 0 takes that form. Okay? And that's the reason why when you, remember, this is the numerator of the coefficient in the McLauring series. Then you need to divide this by n factorial to get the coefficient. That's why you have that definition there. Okay? So if you want 1 plus x to the r, what is this? So this is going to be the sum from 0 to infinity of r choose n, x to the n, where we define this as follows. So at 0, this is 1. At 1, when n is equal to 1, this is equal to r. And otherwise, for n greater than or equal than 2, we define this as r times r minus 1. It actually works for n greater than or equal than 1. I'll show you. Basically, this is telling you when to stop, okay? So when you have your n, let's say that you have n equals 1, right? So if n is equal to 1, you just plug it into here. When n is 1, this cancels, and then you get r. So you stop exactly here. If n is equal to 2, so what's r2? So what's r choose 2? What is this guy? That means that you put a 2 here, and then negative 2 plus 1, that's negative 1. So you stop right here at r times r minus 1, okay? So it's pretty simple. And then that will be over 2 factorial, and so on, okay? So the series, you can write it, to really understand it, you can write it as 1 plus, that would be rx. Then when n is equal to 2, which is the x squared term, you're going to have r times r minus 1 over 2 factorial. Who can tell me what's the coefficient of x cubed? I have an x cubed here. What comes in front? r minus 1, r minus 2 over 3 factorial. So you stop 1 less than the power. Okay? So what you subtract in the r, you stop 1 less than the power, and then you do x cubed, and so on. Okay? So as a homework, try this, because you have to be able to do this, okay? See if you can find the series for the square root of 1 plus x. Let me see, let me tell you what the answer is, but then make sure that you convince yourself of that and that you can verify on your own, okay? So solution is, so the answer is that this guy is going to be equal to, of course, here we're taking r to be 1/2. So when you take r equals 1/2 in there, you're going to get 1 plus 1/2 times x, and then the sum from 2 to infinity of negative 1 to the n minus 1, then you get 1 times 3 times 5, all the way up to 2n minus 3, divided by 2 to the n times n factorial, x to the n. So if you plug in the above formula, in this formula, r equals to 1/2, this is going to come up. Okay? So make sure that you can do the algebra and that you understand where the 1 times 3 times 5 times 12 minus 3 are coming from and so on. All right? Okay, so I guess that's it. I wanted to do more, but this is where we stop. Okay, any questions?
When like you're writing r over n or r over 2, what does that mean?
I just told you what that means. This is the definition. It's just that in general, when r is an integer, for example, in combinatorics, you can write something like this.
Wait, what did you call it?
Combinatorics, you can write this is combination. This is the same thing, probably there's another notation that could be more familiar to you, 4C2. So what this does is it counts how many different ways you can pick two objects out of 4. So let's say that you have 4 books. How many different ways you can pick 2 books out of that pile? Like the first and the second one, the first and the third, the first and the fourth, or the second and the third, the second and the fourth, and so on. How many different combinations? How many different ways you can choose that? There's a way to compute this. This is 4 factorial over 4 minus 2 factorial times 2 factorial. So in general, n choose k, it can be written as nck. The formula is n factorial over n minus k factorial. Sometimes you see this in precalculus. Times k factorial. But this only makes sense when you are talking about integers and when n is an integer and k is less than n. Okay? That's only when this makes sense. Now, the point is that this matches the following expression. What is this equal to? If I cancel out the first n minus in the factorial on top, this is 1 times 2 of the way of 2n, right? If you cancel out the first n minus k terms in here, what remains? n minus 1, n minus 2, all the way up to the one that comes right after n minus k. What comes right after n minus k? N minus k plus 1. So that expression equals this. And if you look at this, that's exactly this. Because instead of k, I'm putting n here. That's exactly the same. So this is a generalization of what we have below, but now here we allow r to be whatever. It could be a fraction, a negative number, whatever you want. Okay? It's just that then it loses the meaning of combinations. But when r is a positive integer, when this is a positive integer and this number is less than this one, then this has a meaning. How many different ways can you choose k objects out of n, in which the order doesn't matter? That's what it does. But it's called combinations. Okay? But what does this mean? I just defined it for you here. That's why I was doing that, because when you look at this list, you may not understand what this is. Because because it's a long formula, we just write this, but you need to know exactly what this is. Okay? And that's the definition. So when it's 0, we define it to be 1. And when it's 1 or larger, this is the formula. It's basically the product from r all the way down to r minus n plus 1 divided by a factor. Okay? And the interval of convergence is from -1 to 1. So you will have questions on this on the homework, so you'll be able to practice. If you have questions, you can come next week and ask me in the office. Okay? I have office hours as usual, so you can come and talk. All right. Any other questions?
Earlier you've been going over the derivatives of 1 plus x to the r power. You had the derivative of x equals r times 1 plus x to the r minus 1.
Yes.
And plugging 0 in for x, you got r.
Yes.
It would be r. Oh, right. It would be 0 to the
Just
r.
get 1. You just get 1. In all of these things, you always have 1 plus x to some power, but when you plug in 0, that's just a 1. So the only thing that survives is the coefficient.
Yeah.
And what's the coefficient? The r, then r times r minus 1, then r times r minus 1 plus r minus 2.
I was thinking the r minus 1 power and then goes to r.
So that's why we get these things here. See, I wanted to do this because otherwise when you see a formula, you're like, where are these things coming from? Well, they come from just taking the derivatives.
Yeah, my free calculus confidence